Hello everybody. Welcome to our first lesson here in geometry. Okay, we're going to be discussing the Unit 1, Tools of Geometry. We're doing square roots and simplifying radicals. Okay, so if you notice in the top part here, I've listed all of your perfect squares. Okay, it's important that you still try to memorize these things. It'll make things a whole lot easier when simplifying radicals and dealing with square roots. Okay, because if you can recognize those numbers, you might not have to use the hockey stick method. Okay, which I will demonstrate both methods, and I'll leave it up to you guys to decide which one you prefer. Okay, so these perfect squares, all right? To be a perfect square means it's just some number that's multiplied by the same number twice. So 1 times 1, 2 times 2, 3 times 3, 4 times 4, so on and so forth. Okay, and so if you look down below here, we got 144, or square root of 144, square root of 225, and the square root of 81. Okay, so what this looks like really is 12 squared, and we're taking the square root of it, right? Now, when we were discussing a squared plus b squared equals c squared, all right, when you're talking how do you get rid of an exponent of 2, you know, when something's squared, we take the square root of it. Kind of undoes it, right? So in this case, when you take the square root of 144, we're really undoing that square on that 12, and we're just left with 12. All right, so you come over here. This is just 15 squared. Take the square root of 15 squared. Those cancel. You're just left with 15. And finally, take the square root of 81. That's just 9 squared. That cancels, and you're just left with 9. Okay? So it's important that you guys remember or memorize these things. It'll save you a whole lot of time down the road. Excuse me. I'm taking a drink of water. All right. So, a radical expression is an expression that contains a square root. The expression is in the simplest form when the following 3 conditions have been met. So, no radicands have perfect square factors other than 1. No radicands contain fractions. And no radicals appear in the denominator of a fraction. Okay? So, what do I mean by radicands? What I mean by radicands is just the answer you get when you try to simplify these things, okay? So down here are some examples of some radicands, okay? And the reason why they're called that is because they're not perfect squares, all right? They don't have, they're not going to be a nice number, all right? So anytime you see a number underneath a radical that is not a perfect square, you know that that number is going to be irrational, okay? And if you don't recall what irrational means, irrational is just a number that is some sort of decimal number that doesn't have any sort of pattern, and it continues on forever. Okay? So these 3 conditions need to be met when solving these things, or when simplifying these expressions. And I'll discuss them as I continue down through. So no radicands have perfect square factors other than 1. They don't contain fractions, and there's no radicals appear in the denominator of the fraction. Okay, so the first part, product property. Okay, what this states is for 2 numbers, a and b, greater than or equal to 0, which means they cannot be negative, we get this property. Square root of ab is equal to the square root of a times the square root of b. So what this property allows us to do is it allows us to break up any factors underneath the radical, okay? So this answer is still the same as this, or this expression is still the same, okay? We're just kind of expanding it, if you will, all right? So, last year, okay, we taught you guys the hockey stick method, okay? And so I'm going to do the hockey stick method a couple times, and then I'm going to, well, I guess I'll just do the hockey stick method. What the heck? Okay. So the reason why I'm circling those, I'm just trying to memorize which problems I want to do. Okay? So on this one right here, so if we do the hockey stick method, what that means is we're using prime factorization to simplify these radical expressions. Okay? So what you want to do is, here's your prime numbers. These are the ones you're typically going to use. Okay? I guess I'll put 11 on there, but you don't see 11 a whole lot. So take a look at this one. So you want to look at of those prime numbers, what's the largest one that can go in there? And so that would be a 5. Okay, and make sure you put those prime numbers on the left. Okay, so the next part, whoops. All right, we got a 9 here, so 9 is divisible by 3. All right, 9 is equal to 3 times 3. And now we have all prime numbers, so I draw my hockey stick. All right, I bring out a 3, and 5 was left behind, and so that stays underneath the radical. And that's our answer. Let's go on to the next one. Okay, square root of 20. All right, hockey stick. So I'm going to go 2, 3, 5, and 7. So 5 is the largest that can go in there, which is just 5 times 4. 4 is just 2 times 2. Hockey stick. Bring out a 2. And there's our answer. Okay. What this property is saying, which we will use, okay, as we go further into the lesson here, what this property says is that square root of 20 is also equal to 4 times 5, right? So I didn't change anything, right? I still got the same numbers, all right, still same value underneath the radical. But now using this property, I can separate those. So I got the square root of 4 times the square root of 5. Well, we know what the square root of 4 is. Square root of 4 is one of our perfect squares, so that's a 2. And we still end up with the same answer, okay? So hockey stick method works 100% of the time. Eventually, though, we would like to see you guys start to recognize which perfect squares go into these numbers. And honestly, I think both of them are just as efficient either way. So let's move down to the one down below here, okay? Now, we know the square root of 45 is already equal to, whoops, does that let me, oh my gosh, 3 square root 5, okay? Now we got to worry about this x. So what I always do with these letters is I write them off to the side, okay? If I got a pair, pull one out, move that to the front. 3x square root 5. Okay? So anytime you see these letters here, I just think it's easier just to write them off at the top and do your pairs that way, okay, until you get comfortable with pulling these things out. So 48. Okay, so 2, 3, 5, 7. Okay, so I know a 3 goes in there. That's 3 times 16. I know a 2 goes in there, so 2 times 8. I know another 2 goes in there, it's 2 times 4. 2 times 2. Here's our hockey stick. Circle your pairs. When you cross them out, bring them out. So we got 2 times 2. Write it off to the side here, so 2 times 2. And the 3 gets left behind. Okay, now we got to figure out what to do with these letters in here. So that's why I was telling you to do this. So there's 3 x's, there's 4 y's, and we already know that z is going to get left behind because it's only got 1. Okay, so I'm going to put the z right down there. And I see 2 pairs of x's, so I bring one out, put one back in, and I see 2 pairs of y's, so I bring some out, y squared, and nothing gets left behind. So let me straighten this up down here, okay? I should have just multiplied those two. So those two 2's get multiplied together. So that's 4x, y squared, and what we have left underneath the radical is the 3 and x and the z. And so that is our answer. Okay, let's keep going. Quotient property. Okay, what the quotient property states is that for any two numbers, a and b, both of them greater than or equal to 0, okay, square root of a over b is equal to square root of a over the square root of b. Okay, so just like with multiplication, this property allows us to separate that fraction, so we have a square root on the top and a square root on the bottom. Okay, and so we'll find this property useful as we dive into some of these other problems down here. Okay, so the first one here. So I'm going to use that property. So I'm going to go 25 with the square root of 16. Square root of 25 is 5. Square root of 16 is 4. And we're done. Let's look at the next one. So I'm going to separate those out. So square root of 100 divided by the square root of 25. We get 10 over 5. Which is 2. Now, if you're also like, well, isn't 100 divisible by 25? Sure is. So, underneath the radical, you get 100 divided by 25, which is just 4. Square root of 4 is 2. So there's a couple ways you could do that one. Let's move on. So let's try this one here. Okay. So what I'm going to do first is I'm going to separate these two things. Okay, now you're thinking, oh crap. This 288 is not divisible by 147. So if you thought you could try that already, that one did not work. Okay. So how do we want to solve this? Well, we could do the hockey stick method for 288, right? It's going to take us a while. Okay. But if we think about this for a second, right, here's a little trick for you. So if you divide 288 in half, take 288 divided by 2, we get 144. Wow, uh-oh. So wait a second, isn't 144 one of our perfect cubes? It sure is. All right, so 288 is just equal to 144 times 2. And then I separate that out. So 144 times the square root of 2. Square root of 144 is 12. And so our top numerator is that right there. Let's take a look at our denominator. So our denominator doesn't have a really nice number, does it? So we're going to go 2, 3, 5, and 7. Okay, so let's see if 7 goes into 147. 147, whoops. It does. Cool. So we go 7, 21. Well, 7 can go in there again. So 7 and 3. Here's our hockey stick. It's got a pair of 7s, so we can bring that out, and the 3 stays behind. So our answer so far is square root, or 12 times the square root of 2 over 7 times the square root of 3. Okay, but we're not done here yet, though, because one of our conditions was that we cannot have a radical expression in our denominator. So, in order to get rid of that, okay, we have to multiply the top and the bottom by square root 3. You're probably thinking, why on earth would you do that? Well, let me show you. Okay, so let's say we're just multiplying these both together, just its own separate problem, all right? So square root 3 times square root 3. Well, using our product property, those go back underneath the radical. 3 times 3 is just 9, and the square root of 9 is 3. So, by multiplying square root 3 over 3, which, mind you, is still just 1. It's one of those math tricks where we're using little tricks to get what we want, okay? By multiplying square root 3 over 3, I'm not breaking any rules, all right? And it gets that denominator, that radical on the denominator to cancel. All right, so let me get some room here. So this is going to be 12 square root 2 times square root 3 over 7. And square root 3 times square root 3 is just 3. I'm going to move those underneath the radical and multiply them together. So it's going to be 12 square root 6 over 21. And if you were to type that into your calculator, if you went square root of 288 divided by 147, you would get 1.399. And then if you did, in parentheses, 12 times the square root of 6 divided by 21, you get the same exact answer. So this is still equal to this. Okay? So just remember that. We're just simplifying this expression. Okay. This one is a piece of cake here, right? Let's think about this. Okay? You're probably thinking, well, we can't really do that yet, right? We can't just divide the square root of 16 by the square root of 8, but we can move those both underneath the radical. And what's this 16 divided by 8? Well, that's 2, and we're done. Done with that one. Let's take a look at this one down here. Okay, 149y divided by, the square root of 149y divided by the square root of 121y cubed. Okay, so what I'm going to do first, all right, is I'm going to separate this 49, separate this y. I'm going to separate this 121. I'm going to separate that y cubed. Okay, the reason why I did that is because these are perfect squares, right? Okay, so what I'm going to do, this is going to be the square root of 49 is just 7, square root of y. Square root of 121 is just 11. Now, if you recall, we got 3 y cubes underneath that radical, so y cubed, y cubed, y cubed. You got one pair, so we're going to bring one out. One gets left behind. And oh shoot, look at this. We got square root of y over square root of y. Those can cancel out. And our answer is 7, 11, y. Okay, 3 more problems. Okay, so going back to what I was talking about up there, all right? Rationalize the denominator of a radical expression is a method used to eliminate radicals from the denominator of a fraction. To rationalize the denominator, multiply the expression by a fraction equivalent to 1 such that the resulting denominator is a perfect square. Okay, so what that means is we're multiplying the bottom by whatever number we have here on the bottom here, okay, which creates a perfect square. Now let's do number 2 first here, because this one's going to be easier, right? So we got a radical on the bottom, so if I multiply the top and the bottom by square root 3, what happens? So what you get on the top, we get square root 3 times square root 3. We can move those both underneath the radical, so you get 3 times 3. 2 times square root of 3 over square root of 9. And the square root of 9 is just 3. Okay? So that's the process we're taking in order to get rid of that radical in the denominator. So let's go back over to this one. Okay? Now we could multiply the top and bottom by 48. All right? The reason why I'm not going to do that is because we're still going to have to simplify that expression anyway. So let's simplify the expression first. So we're going to go, does 3 go in there? I'm pretty sure, right? 48, yeah. 16, right? So we're going to go 3 times 16. I'm going to go 2 times 8. I'm going to go 2 times 4, 2 times 2. And I'm pretty sure we already did this one earlier. Okay, so there's our pairs. So we got 3 over 4 square root 3. And now, we'll multiply the top and the bottom by square root 3. The top we get 3 square root 3 over 4 times 3, which is 3 square root 3 over 12. Continue to simplify. Square root 3 over 4. Okay, and if you were to punch that into your calculator, so you go 3 divided by second square root of 48. And then we go second square root 3 divided by 4. You get the same exact answer. Okay. Last but not least, let's start over here. Okay, so what I'm going to do is I'm going to separate these. 13 times the square root of y over square root of 18 times the square root of y. The reason why I did that is these will cancel. I'm left with square root 13 over square root 18. Still not done yet. Okay, so what I'm going to do first is I'm going to simplify this expression down here. 13 is a prime number, so luckily we don't have to do anything in the top. At the bottom we do, so I'm going to use my prime factorization. So I'm going to go 2 times 9, 3 times 3, hockey stick. So we're going to bring out a pair of 3s. So we're going to have square root 13 over 3 square root 2. And now we got a much smaller radical to multiply everything with. Okay, so I'm going to have to write this over here. All right, so we're going to have square root of 13 times square root of 2 over 3 times 2, which is square root 13 times 2. Make the radical, this is 6. And finally, 13 times 2 is 26. So we get square root of 26 over 6. And that is simplified as it goes. Because you got to figure 13 is a prime number, so we would have nothing but prime numbers in there, so we can't use the hockey stick method for that last one. So that is your first lesson in square roots and simplifying radicals. Try those homework problems in the bottom here. All right, so I'm going to say try the ones I've circled here, okay? Okay, try those 6 problems. Okay? You can cross these ones off.